Hello everyone and welcome back again to the linear algebra component of the Calculus and Linear Algebra series. In the last video we introduced this idea about how the complex numbers act on the complex plane via division, and we saw that had the opposite effect to how they acted on the complex plane via multiplication. So recall they acted on the complex plane via multiplication by rotating the complex plane of whatever the argument of that complex number was, and then stretching the complex plane by the modulus of that complex number. And they acted on the complex plane via division by just doing the opposite of those operations. That is, we rotate by minus the argument of the complex number and then squish by the scale factor of the modulus of z. And what we want to do now is we want to say, is there some general formula that we can write down for taking multiple powers of complex numbers? That is, if we take a complex number z and we raise it to some power z to the power of n, say, where n is an integer, is there a general way in which we can find that kind of expression for z, or z to the power of n, given that we just know what z is? And we can just think about this geometrically, that's kind of fairly clear what we're going to get. That if we take z, for example, as a complex number, and we multiply it by itself, all that's going to do is rotate that complex number by the argument of z and stretch it by the modulus of z. But if we look at the special case, where the modulus of z equals 1, that would mean that we stay a constant distance away from the origin, because if we just keep multiplying by the modulus of z, which equals 1, that's the same as just doing nothing, right? It just leaves everything the same. Multiplying by 1 doesn't change the length of that vector. But what it does do is it just rotates me constantly around the complex plane by some constant angle, which is the argument of z. So if I say that the argument of z is theta, then z to the power of n is just going to have argument n theta. So we can actually deduce a theorem, a kind of famous theorem about this, which is known as Dimorphs Theorem, and see if we can say, well, is that actually going to be true for all n in the integers? So I'm going to go to my tablet now, and we're going to kind of write down some statement here, or our theorem. So our title here is that we've got Dimorphs Theorem. So we write Dimorphs Theorem. Now, what is Dimorphs Theorem? It's effectively just this version of what I just said a minute ago. So if we write down our theorem, our theorem effectively says, so let z equal cosine of theta plus I sine theta. And if we think about that, what all that's doing is that's just giving all the complex numbers that lie on a circle of radius 1 centered about the origin. So all complex numbers that lie on that circle are going to take this form, and I can just put in some whatever kind of value of theta I put in would give me one of those complex numbers on that circle. Okay, and then we want to say, what is then z to the power of n? So z to the power of n is going to equal cosine of n theta plus I sine of n theta. And we're going to, at the moment, just restrict ourselves to the case where n is a natural number, and we'll extend in a moment to the entire integers. So this makes sense from what we just talked about a minute ago, that this seems like a reasonable hypothesis to check if that is true. We've got here that when we multiply two complex numbers, it just moves me around the complex plane by this constant angle theta, and because the modulus of the complex number is 1, it doesn't stretch in any way as I multiply around. In other words, it leaves me at a constant distance away from the origin, which is why I continue to lie on a circle. Right? If I'm a constant distance away from the origin on my complex plane, then I must be lying on a circle. It's effectively the definition of a circle. Okay, so how are we going to prove this? Well, we're actually going to prove this using some induction. Specifically, we're going to use a weak proof by induction. So let's kind of go back to some first order logic and see if we can write this statement in first order logic symbols, just to kind of keep reinforcing this point. So the statement can be written as, for all n in the naturals, P of n, where P of n is the predicate, effectively our statement up here, which is z to the n is equal to cosine of n theta plus I sine of n theta. Now, if I'm wanting to prove this by a weak proof by induction, the first thing that I need to do is I need to show a base case. And the base case is I need to show that P of S is true, where S is the least element of our domain of discourse. Our domain of discourse here is the natural numbers, so the least element is 1. So I need to simply show that P of 1 is true. So is P of 1 true? Well, clearly P1 is true simply from the definition of Z. In other words, we've said Z is cosine theta plus I sine theta. If I put n equals 1 into this formula, I get cosine theta plus I sine theta. So indeed, it is true. Z to the power of 1 equals Z. Okay, so now I want to assume that it's true for some n in the naturals and see if I can show that it follows that P of n plus 1 is true. So I'm going to assume that P of n is true for some n in the naturals, and I want to then show that P of n plus 1 is true. So assume P of n is true for some n in n. Then what? We need to show that P of n plus 1 is true. So let's start with that. We're going to have Z of n plus 1. Well, that by definition, right, is Z to the n times Z, just using our rules of exponentials. And we can substitute in the fact that we've assumed that P of n is true up here, right? We've said that this P of n is true. Hence, we can substitute in for Z to the power of n as cosine n theta plus I sine n theta. And we multiply that by Z, which is cosine of theta plus I sine of theta. Okay, but we know the definition of how to multiply two complex numbers in polar form. That is, we just simply take the arguments in these corresponding cosine and sine terms and we just add them. So just adding those together, we get cosine of n plus 1 theta here, where I've just factored out the theta term, plus I sine of n plus 1 theta. In other words, I've proven that if P of n is true, then P of n plus 1 is true, because this is exactly my statement that if this thing is equal to this thing, then that's effectively showing that P of n plus 1 is true. So, let's say hence, it follows that what we've proven that for all n in the naturals, P of n implies P of n plus 1 is true. And it's true for every n simply because we didn't make any conditions or assumptions on n. We just said it's true for some n, and then we proved that it must be true for n plus 1. Or P of n plus 1. So that is true. And we said by the principle of weak induction, it follows that the initial statement is true. In other words, for all n in n, P of n is true. So that is our finished proof, and we'll put a little box here at the end to say that our proof is complete. So we've proven this statement that we suspected was true just by thinking about the geometry, at least for the natural numbers. We've shown it for the domain of discourse for the natural numbers. But we also suspect that this might be true for kind of the whole integers, right? It seems fairly clear that it's going to be true for when n equals 0, but it also should be true for when I take z to negative powers, because I want to think of multiplying kind of negative powers of z. So I take kind of z, say to the power of -2. That's going to be like 1 over z times 1 over z. In other words, that's kind of the same as doing division twice by z. And if I think about that one, all that does is that I now, instead of adding up the arguments, I just take away the arguments and divide again by the modulus of z. But the modulus of z here we're going to consider is 1, so it's still dividing through by 1. That means that the vector is unchanged, it's constant away from the origin. And if we just keep dividing by those things, that means we just keep removing angles of theta. In other words, we should get that instead of having a plus n here, we would have a minus n. So let's write that down as our kind of theorem. So this is still Dimorphs Theorem, we're going to call this. So we'll write this as Dimorphs theorem. And then we'll just make a little note here. This is for the whole integers because it's different to the previous one. The other one was just for the naturals. Okay, so if we have, what's our statement of our theorem? It's exactly the same as before. Apart from now, we're going to take our domain of discourse as the integers. So that is, we let z equal cosine theta plus I sine theta. Then what's z to the power of n? We say z to the power of n is cosine of n theta plus I sine of n theta. But now we're going to take for n in z, not in the naturals. How do we prove this one? Well, we've already shown, right, that it's true for the naturals. So it has already been shown true for n in z, n in n, the naturals. And that's just our positive integers. So that's kind of a kind of decent number of cases we've proven. In fact, an infinite number of cases. But we want to also extend it to all the negative integers and for 0. Well, it clearly follows for when n is 0, right? Because we've got on this side, we're going to have z to the power of 0, which is going to be 1. And we have here that we've got cosine of 0, which is 1, and sine of 0, which is 0, and I times 0 is 0. So it clearly follows. So it is clearly true for n equals 0. Right, that one's just a singular case that we can check. Now, we want to prove it for all the negative integers. So now, let n start here with it being greater than 0. Then what we're going to do is we're going to take z to the power of minus n. So taking z to the power of minus n, we can realise just using some rules of powers, that's the same as z to the power of n, all raised to the power of minus 1. But we know what z to the power of n is here, right? Because n is simply just a natural number, because we've taken n to be greater than 0. So we can write that simply now as cosine n theta plus I sine n theta. And this is the whole thing raised to the power of minus 1, right? And we've just used our previous proof before that we've shown that that is true already for when n is natural. But can we find a way of writing z to the power of minus 1 in a way that's in terms of multiplying copies of kind of the complex conjugate of z and the modulus of z? Well, we already saw that in the division video, but we can think of z to the power of minus 1. So acting via on the complex plane via division of z is the same as multiplying by z bar, the complex conjugate, and then scaling down by a factor of the modulus of z squared. So if we use that formula, we can substitute it into here effectively, into this thing. Well, we realise that we've got here that this is effectively our z to the power of minus 1. This is a kind of general formula. So it follows that z to the power of minus n, we simply complex conjugate this thing and then divide it by the modulus squared. But the modulus squared is equal to 1, so we simply just take the complex conjugate of this thing. So in other words, we get cosine of n theta minus I sine of n theta. Because we recall that the complex conjugate just reflects that complex number through the real axis, which is equivalent to just flipping the sign on the I term. Okay, well now we can just use the fact that cosine is an even function. In other words, cosine of theta is the same as cosine of minus theta, so we can put in a minus sign in here and that's identical, that's unchanged. And sine is an odd function, which means that sine of minus theta is equal to minus sine of theta. So we can take that minus sign inside to get this. In other words, right, we finished, right? We've got here that z to the power of minus n is the same, or we can write it here, z to the power of minus n is cosine of minus n theta plus I sine of minus n theta. So we've shown it for the naturals, we've shown it for the negative integers, and we've shown it for 0, so we're done. So we can put our nice little square box to say that we've finished our proof, and that Dimorphs theorem holds for all n in the integers. So that's our complete proof. And how's this going to be useful? So now let's look at some examples. I give you some specific complex numbers, and then we want to raise them to some powers that you don't want to expand out huge brackets. We can just write them in polar form and then use Dimorphs theorem to find out what the kind of z raised to that integer power is. So it's quite simple. Or you can also just think about it using a kind of geometric picture. So kind of connect together this algebraic way of doing things and this geometric way of doing things. So let's call this examples. And we will go down here to write our example 1. So I'll only go through one example here, and you can look at some more examples within the notes down there, and if you have any questions, do email me. So let's move that back to where we were. So if we let z equal, let's say 1 plus I, because that's a kind of nice complex number to look at. If we think about where that lies on the complex plane, we can kind of draw our complex plane over here. This is our imaginary axis. This is our real axis. We go 1 unit along and 1 unit up. So that is, we go I here and 1 along. In other words, it lies somewhere like here. This is the point 1 plus I. And we realize that this is effectively just, if I cut a 1 by 1 square in half, this is what would give this triangle. And this, in other words, is bisecting the angle of 90 degrees. So this is 45 degrees, which in radians is pi over 4. And it just follows from some simple Pythagoras theorem that this length here is root 2, right? Because we've got 1 along and 1 up. So this modulus of this complex number is root 2. So we can instantly write it in polar form. Here z is root 2 cosine of pi over 4 plus I sine pi over 4. And let's say we want to find this complex number raised to the power of 4. So then what is z to the power of 4? Well, z to the power of 4 now, we can use Dimorphs theorem to just put the 4 into these sine and cosine pieces. And if we just think about, again, what happens if I multiply a complex number multiple times, all I do then is I keep scaling each term by a factor of root 2. So in the previous case, we just looked at the situation where the modulus of z was equal to 1. So that is, it just left us on the unit circle when we multiplied it multiple times. But in this situation, it's going to kind of wind us round the complex plane by this constant angle here of pi over 4, 45 degrees, but also stretch it by a scale factor of root 2 each time. So in other words, I'm going to get something like root 2 to the power of 4, and then I can just apply Dimorphs theorem here to get the following. So I can take that power of 4 into our sine and cosine pieces. Root 2 to the power of 4 is simply going to be 2 squared, which is the same as 4. So I get 4 cosine of pi plus I sine of pi. Cosine of pi is minus 1, sine of pi is 0, and 0 times I is 0. So in other words, I've got 4 times minus 1, which is minus 4. So that's a way of calculating from this complex number that we had here, this z. We can find what z to the power of 4 was, just using Dimorphs theorem, and we didn't have to expand this thing doing some kind of huge binomial expansions. It immediately followed just from Dimorphs theorem. And Dimorphs theorem we saw intuitively coming from the geometry. So let's make sure that this makes sense as well in terms of our kind of geometric picture. So if we go up here and we're thinking about this complex number here, this 1 plus I is z, if we do z squared, what's that going to do? That's going to take us by 45 degrees this way, so that's going to take us over to the imaginary axis, and then it's going to stretch this vector here, by another root 2. So in other words, it's going to take us now to the number 2i, right? Because it's going to be root 2 times by this vector here rotated by 45 degrees. And then we rotate it again to another 45 degrees, which is going to take us here. So that's going to give us kind of our z cubed. So that's taking us over here. And then z to the power of 4 is going to take us to another 45 degrees, which is going to take us somewhere in the negative reals, which is exactly what we kind of got here. We saw that we got indeed a negative real number. And each time we just kept stretching that vector by a factor of √2. So when it went to here, it's stretched by √2, in other words, taking it to of a length 2. When it goes along here, it's stretched by another length of √2, which made it of length 2 √2. And then when it came down here, it's stretched by a length of 2 √2 times √2, which means it's got length 4. So it's got length 4 out here, and it's rotated round by this angle. So that's exactly what we got here, right? We saw that it was -4. In other words, we've seen that it was in the negative part of the real axis, and it was of length 4. So that's where we're going to conclude the video. And in the next video, what we're going to talk about is we're going to talk about another way of writing complex numbers in what is known as the exponential form, and arrive at kind of a very famous formula known as Euler's formula. So again, I remind you to kind of complement this by reading the notes alongside these videos. There's some more examples in the notes in there and some kind of other explanatory detail, and to attempt any problems in the module handbook relating to this video. So thanks very much for watching, and see you in the next video.